6:15 a.m., October 14, 1943. Cold morning air clung to the metal fuselage as the first rays of sunlight slid across a quiet Luftwaffe airfield in western France. The frost had not yet melted, and every footstep echoed with a brittle crunch. Mechanics in heavy coats moved through the dim glow of hangar lamps, their breath turning to thin clouds as they whispered to each other. In the distance, the muffled rumble of a generator hummed through the stillness, mixing with the faint smell of oil, cold steel, and damp canvas. A strange aircraft sat in the center of the hangar, a hulking shape, its silhouette unlike anything the Germans were used to. They had spent the entire night dragging it in from the forest clearing where it had crash-landed. Now, as they circled it, some with flashlights, some with notebooks, they realized they were looking at a machine that should not exist. It was a captured Republic P-47 Thunderbolt, the American fighter the Luftwaffe had heard plenty about, yet understood very little. The one thing they did know was that pilots had begun whispering rumors. The Thunderbolt could dive so fast that it sometimes outran German fighters that tried to pursue. But seeing the aircraft this close, covered in mud and pine needles, its massive frame bent but not broken, created a wave of disbelief among the mechanics. The wings were intact, the rivets still held. Even the skin panels looked surprisingly unscarred for an aircraft that had plunged into the forest at the end of a high-speed dive. As the sun rose higher, more officers arrived, some rubbing their hands for warmth, others blinking away exhaustion. In their minds, one question kept repeating: how could this machine survive the kind of dive that would rip most fighters apart? The sound of tools clicking open, the hiss of lanterns, and the scrape of metal being lifted filled the air. These weren't casual repairs. This was forensic inspection, an attempt to unlock a mystery that German engineers had only theorized about. Meanwhile, hundreds of kilometers away, the skies over Europe were becoming the battleground where this mystery mattered the most. By late 1943, the Allied bombing campaign was intensifying, and with every passing month, the P-47 Thunderbolt grew more important. It escorted B-17s deep into hostile territory and returned, often bearing scars of combat, but rarely the wounds of structural failure. German pilots had noticed another pattern they couldn't explain. Thunderbolts dove into clouds or toward the ground at terrifying angles, and when German fighters tried to follow, their airframes began to shake violently, sometimes even shedding parts. The P-47, somehow, did not. Back in the hangar, the examination became more urgent. A senior engineer, a man who had worked on the Bf-109's wing structures, tapped the leading edge with his knuckles. The sound was solid, far heavier than a German wing. He narrowed his eyes and ordered the mechanics to remove a panel. When they did, they paused, stunned by what the flashlight revealed. The internal spars were massive, not just strong, oversized. It looked more like the internal structure of a light bomber than a single-engine fighter. A man muttered under his breath, comparing it to the spars of a U-87 Stuka. Another questioned why the Americans would waste so much weight on a fighter's wings. The answer was simple but revolutionary. The plane had been designed for a very specific purpose: high-speed diving, stability at extreme velocities, and structural endurance far beyond normal fighter expectations. The Germans had approached fighter design with the philosophy of agility and climb performance. The Americans, however, had created something closer to an airborne hammer, a machine built to deliver devastating firepower, survive punishment, and escape when needed by simply plunging into the sky. Before this morning, the Germans knew the Thunderbolt was big. They knew it was heavy, but they did not know what its wings were hiding. To truly understand why this moment mattered, we need to pull back from the cold hangar in France and return to the earliest sketches of the P-47, back to a time when the United States Army Air Corps urgently needed a long-range escort fighter that could protect bombers not only at altitude but also during emergencies, breakaways, or steep defensive dives. Engineers at Republic Aviation had studied combat reports from Europe and Asia, and they saw a pattern emerging. Aircraft that could not handle high-speed dives were suffering catastrophic failures when pushed beyond their limits. Throughout the late 1930s, structural engineers had repeatedly confronted a terrifying aerodynamic phenomenon: compressibility. At high speeds, approaching the transonic range, shock waves could form erratically over a wing surface, stealing control authority and increasing stress loads far beyond what traditional structures could bear. Fighters like the early Spitfire and Bf-109 occasionally encountered these limits when diving to escape hostile aircraft. Their wings would flutter violently, control stick pressure would spike, and pilots often had no choice to level out early, sometimes too early to avoid an enemy fighter closing in behind them. The Americans, studying wind tunnel data, believed they had an answer: brute strength. If a fighter had to dive rapidly, to attack, to evade, or to pursue, then its wings and control surfaces needed to be engineered with a safety margin so large that even transonic shock formations could be endured. It wasn't elegant, it wasn't weight efficient, but it worked. This philosophy birthed the Thunderbolt. Republic Aviation constructed a fighter that looked oversized to European designers: a thick elliptical wing, built around two massive spars, skin panels that were thicker than most fighters used, and a rugged fuselage wrapped around a turbo-supercharged radial engine. Early critics mocked its bulk, calling it more of a flying tank than a fighter, but the Americans stayed the course. German intelligence officers, scanning Allied engineering reports before the war, dismissed the approach as impractical. They believed agility would always trump size. But by 1943, their pilots were coming home with stories that challenged everything they thought they knew. When a Thunderbolt dove, even the fastest Focke-Wulf 190 struggled to keep up. Luftwaffe manuals warned pilots not to exceed certain dive speeds, as the FW-190, especially the early variants, risked severe compressibility issues. Meanwhile, American test pilots reported the Thunderbolt surviving dives that touched 500 miles per hour and beyond. The aircraft shook violently, yes, but its wings held. That was the part the Germans couldn't fathom. And now, standing around the captured aircraft in the hangar, they had the chance to inspect the evidence firsthand. A mechanic slid his hand along the wing root, feeling the cold aluminum. It was thick, nearly twice what he was used to. Another pointed to the rivet, closer together, denser, and arranged in a pattern that increased structural rigidity. These weren't cosmetic differences. They were the physical manifestation of an engineering philosophy few in the Luftwaffe had ever considered. The senior engineer crouched beneath the wing and studied the flap assemblies. He noted the heavy hinges, the reinforced control rods, the way the structure blended into the spars. Every part seemed designed with one concept in mind: survive loads that would tear a lighter wing apart. He scribbled a note, something about safety margins far exceeding what German engineers typically allowed in fighter aircraft. As they continued the inspection, one mechanic opened the top panel where the ammunition boxes sat. What he saw deepened the mystery even further. The internal bracing around the guns wasn't just for mounting the .50 caliber Browning machine guns. It doubled as additional structural reinforcement for the wings. The Americans had effectively turned their weapons mounts into load-carrying structural components, distributing stress more evenly across the wing during extreme maneuvers. That design choice meant the Thunderbolt's wings weren't just wings. They were solid, load-carrying, integrated structures capable of handling both aerodynamic forces and combat stresses simultaneously. Outside the hangar, the sound of distant engines vibrated through the morning air. A patrol was taking off. A few mechanics paused to listen. There was a growing understanding. quiet, subtle, but undeniable, that the aircraft they were studying represented a turning point in the air war, not because of its speed, not because of its firepower, but because of the way it absorbed punishment that would destroy many other fighters. As the Germans removed more panels and examined deeper structural elements, their disbelief only grew. One of them traced the curve of a spar with his fingers, shaking his head in silence. Another compared the Thunderbolt's construction to earlier U.S. aircraft like the P-36 Hawk or the P-40 Warhawk. But those planes, though rugged, weren't built like this. This was something else, a leap forward in strike fighter survivability. The hangar filled with the soft clatter of tools and low murmurs. Lamps buzzed, a mechanic tightened his scarf as a cold gust slipped in through the open hangar doors. They needed answers, and the more they inspected, the more surprising those answers became. Why did the wings show so little damage after a high-speed crash landing? How did the structure remain intact when the aircraft had exceeded speeds many German engineers still considered dangerous? What allowed this fighter to dive with confidence when others hesitated? These questions hung in the air like frost as the inspection continued. And while the mechanics in France were only beginning to unravel the mystery, thousands of kilometers away in the United States, engineers at Republic Aviation already knew the truth. A truth built from wind tunnel trials, flight tests, and the sobering lessons of early war air combat. They had built a fighter that could survive where others failed. A fighter whose strength came not from elegance, but resilience. A fighter whose wings could endure the terrifying forces of a 500-mile-per-hour dive. The hangar lights flickered as a gust of wind pushed through the open doors, rattling loose tools and sending a ripple through the canvas tarps that covered spare aircraft parts. A mechanic steadied a lamp and leaned over the P-47's exposed wing structure. The deeper they went, the more the disbelief spread across their faces. What they were staring at wasn't simply foreign engineering. It was a different philosophy entirely, something no German fighter designer had ever attempted. A lieutenant stepped closer, wiping grease from his glove as he studied the Thunderbolt's main spar. It wasn't the typical narrow I-beam used in the Bf-109, nor the slightly broader structure found in the FW-190. This was thick, almost absurdly so, a massive forging that looked strong enough to support a bomber. The metal surface bore scuff marks from years of service, yet no cracks, no warping. No signs of stress despite the dive forces it had endured before landing in German hands. The lieutenant shook his head slowly. "It shouldn't be this strong," he murmured, his breath fogging in the cold air. "Not on a fighter." But it was. No one in the hangar knew it yet, but American engineers at Republic Aviation had predicted exactly this moment months earlier. They understood that a fighter escorting bombers deep into enemy territory needed options. One of those options was escape. A P-47 pilot who found himself overwhelmed could shove the nose down, tuck in the wings, and dive away at speeds that terrified even test pilots. Some had reported the airspeed needle slamming past 480 miles per hour. Others had seen 500 miles per hour. One pilot near Italy reached a speed so high that the tailplane locked, the controls stiffened, and he nearly lost the aircraft. Yet the wings still held. Word reached the Luftwaffe through combat reports long before they ever touched a P-47. Pilots returning from interceptions wrote about the same thing. The American fighter dove like a stone and did not break apart. Several German pilots had retreated from attacks simply because the vibration in their own aircraft grew too violent when attempting to follow. Compressibility, tail buffeting, sudden tucking of the nose. These aerodynamic monsters haunted every dive of a 109 or early 190. But the P-47, it seemed to endure the same airflow punishment without tearing itself apart. Back in the hangar, a mechanic popped loose another panel and lifted it aside. Dust and pine needles fell to the floor. Inside, more reinforced ribs and thicker skins appeared. He slid his fingers along a rib that connected to the center spar. It felt twice as broad as anything on a German fighter. One of the older technicians crossed his arms and exhaled sharply.
He'd spent years repairing FW-190s with wings that cracked from hard pullouts. Seeing an American fighter built like this felt like an insult, as if the Americans believed weight didn't matter. He muttered something under his breath. "We build birds, they build anvils." But weight, in the Thunderbolt's case, was chosen deliberately. The Americans had trade-offs. Yes, it climbed slower, turned wider, and consumed more fuel. But those sacrifices bought structural strength no other fighter in the war could match. Meanwhile, outside the hangar, the low rumble of a motorcycle approached. An officer dismounted, hurried inside, and handed the senior engineer a worn folder stamped with Eagle insignia. It contained reports from pilots on the Channel front, men who had seen Thunderbolts up close, sometimes too close. One report was particularly revealing. A German pilot flying an FW-190A4 had engaged a pair of P-47s near Cherbourg. When one Thunderbolt suddenly rolled inverted and dove toward the coast, the 190 pilot followed. His cockpit shook violently as he passed 420 miles per hour. The control stick became like wet cement, airframe tremors grew louder. A deep, low-frequency hum filled the cockpit, the sign of compressibility waves forming. Terrified, he pulled out early. The P-47 did not. It continued downward until it vanished into cloud. The German never saw it again. When this report reached commanders, the reaction was frustration mixed with curiosity. How could a heavy American fighter dive faster than the FW-190, which was known for superb high-speed behavior? The answer wasn't obvious until they inspected a Thunderbolt firsthand. Back in the hangar, the senior engineer flipped through the pilot reports as he walked around the aircraft. He wasn't reading for stories, he was gathering data. Each dive, each speed estimate, each description of wing vibrations helped him piece together the puzzle that lay in front of him. At the wing roots, he knelt again. The metal was cold under his palm. He compared what he saw to German manufacturing orders. Their fighters used carefully calculated strength-to-weight ratios, optimized for agility. The Thunderbolt used strength-to-survive ratios, optimized for resilience. He stepped back and observed the entire wing. It was thicker than most fighters in the world. That thickness wasn't accidental. It served three critical functions. It allowed the supercharger ducting to pass beneath the cockpit. It gave room for 8.50 caliber machine guns. And most importantly, it housed the massive spars needed to withstand incredible aerodynamic loads. Nearby, two mechanics opened the ammunition trays. Inside, they saw what engineers called load paths. The gun rails and brackets weren't simply bolted on. They were integrated. During extreme dives, those rails helped carry the distribution of compressive forces along the wing's internal structure. The guns, in other words, were part of the wing's skeleton. One mechanic exhaled, almost laughing. The Americans used their guns as structural reinforcement. Another replied, "We'd never do that. Too heavy." The first one nodded. Maybe that's the point. Meanwhile, in the United States, at Wright Field and Republic's Long Island plant, test pilots were pushing Thunderbolts through terrifying dives to identify limits. Engineers monitored every flight, cameras recording surface distortions on the wings. Some test flights reached Mach 0.72, unheard of for a piston fighter at the time. The pilots reported control lockups and shock waves, but the wings persisted. On one occasion, a test pilot returned with trembling hands and said, "The wings took it better than I did." Those results were sent directly to combat groups, not as bragging points, but as instructions. P-47 pilots were told that their aircraft could survive dives well past 450 miles per hour, though they were warned about the controls becoming dangerously stiff. German engineers reading captured U.S. documents later would see the same conclusion. The Thunderbolt was never meant to be nimble. It was meant to be unbreakable. In the hangar, as noon light began streaming in, the Germans reached the flaps. A mechanic unbolted the hinge covers and pried them open. He examined the actuator rods, then frowned. Oversized. He checked the bearings. Reinforced. He compared the dimensions to those used on the FW-190. "This is twice the weight." The senior engineer scribbled notes. Oversized flaps meant the Thunderbolt's wings wouldn't twist catastrophically under rapid deceleration. It also meant high-speed control was more stable. Then they found something even more unexpected: multiple redundant brackets and ribs supporting the flaps. It was as if the Americans assumed the plane would break unless they added extra reinforcement. But it didn't. Even after dives that pushed close to the transonic barrier, the P-47's wings emerged intact. The hangar grew quieter as the officers gathered. For the first time, they began to grasp the full implications. If the Allies continued escorting bombers with fighters that could escape any pursuit by diving, then the traditional German interception tactics would weaken. German pilots relied on both climb and high-speed dives to position themselves. But if their aircraft shook apart beyond 450 miles per hour, and the Thunderbolt remained solid, then the war was shifting. One of the younger mechanics paused his work and looked up. "What does this mean for us, sir?" The senior engineer closed the folder of pilot reports and exhaled. "It means we're fighting a machine built for a different war than we designed for." Meanwhile, back in the skies over Europe, Thunderbolts continued proving the engineers right. Pilots dove to save themselves from Bf-109s. They dove after ground targets. They dove during escort breaks. In every case, their wings carried them through. German radar operators occasionally logged the sudden blips of aircraft falling at impossible speeds, American fighters descending faster than anticipated. Some German units even issued informal warnings. Do not follow a P-47 into a steep dive unless absolutely necessary. It was not an official order, but pilots repeated it among themselves because the danger was real. Back in the hangar, the examination was reaching its final stages. Sweat mixed with engine oil on the mechanics' hands despite the cold. A few paused to stretch their backs before moving to the next panel. The last space they inspected was the wingtip assembly, the area most prone to stress fractures after high-speed dives. They braced themselves for cracks, warping, uneven rivet lines. There were none. The wingtip was intact, perfectly aligned, solid. That was the moment the senior engineer realized the truth. The Thunderbolt's dive strength wasn't a myth, nor a rumor exaggerated by pilots. It was a measurable physical reality, a reality built into every inch of the aircraft's design. He placed his hand on the wing and stared for a long moment. The hangar felt colder. The buzz of the lights faded. The mechanics waited for him to speak. But he didn't. Because beneath his hand, he felt something that both impressed and unsettled him. A fighter wing built not just to fly, but to withstand forces no German designer had dared to imagine. And somewhere, in the distance, he heard another aircraft take off to the sky. Not German, American. As if the war itself was reminding him that the skies were changing.
The sky above the airfield darkened as a layer of late-afternoon clouds drifted across, turning the metal skin of the P-47 a muted silver gray. Cold air pushed through the open hangar doors, carrying the distant hum of an aircraft engine climbing somewhere beyond the tree line. The German mechanics paused, listening. The sound was faint, but familiar. The deep, rising growl of a radial engine under load. Only this time, it wasn't coming from their captured Thunderbolt. It was coming from a test flight over the horizon. A reminder that while they studied this machine, another one was flying freely overhead. Inside the hangar, the senior engineer stood over the disassembled wing root. He rested both hands on the cold metal, as if trying to absorb its meaning. Around him, the younger mechanics continued packing tools, sweeping dust, and closing inspection panels they had opened hours earlier. Their movements were slower now, their voices quieter. The excitement of discovery had turned into a sober understanding. This aircraft was a problem they couldn't simply engineer away. He stepped back and examined the Thunderbolt from a distance. With panels removed and its guts exposed, it looked less like a fighter and more like a fortress. A mountain of aluminum shaped into a winged machine. The spars, the ribs, the overbuilt flaps, the reinforced hinge brackets, every piece told the same story. It was not designed merely to fly. It was designed to survive. A mechanic handed him one final report, translations of captured American maintenance logs and field test summaries. The engineer flipped through them. Words like compressibility, shock buffet, control stiffening, Mach tuck, appeared again and again. American pilots had been fighting not just the enemy, but the laws of aerodynamics themselves. They had dived into regions of airflow so unstable that only one question mattered: what holds together, and what does not? And for the Thunderbolt, the answer had been the same every time. It held. He closed the folder and set it aside. His eyes drifted back to the wing spars. The metal gleamed faintly under the lamps, reflecting the subtle tremble of the bulbs. For a long moment, he imagined what it would feel like to sit inside such a machine, to shove the throttle forward, hear the turbo supercharger spool up, watch the airspeed needle climb past every warning mark, and trust your life to a structure built like this. Would fear vanish? Or would the speed amplify it? Outside, the distant engine sound faded. Silence returned to the hangar, heavy, metallic, tense. Then one of the younger mechanics broke it. "Sir, do you think this is why their pilots dive so fearlessly?" The senior engineer looked at him. His answer came quietly. "They dive because they know the aircraft will return with them." That truth reached beyond engineering, beyond tactics, beyond the war. Meanwhile, hundreds of kilometers away, deep over Europe, Thunderbolts escorted bomber formations through frozen winds and flak storms. The men flying them knew the stories. They knew what German fighters could do in steep dives, but they also knew what happened when they pushed the nose down and let gravity take over. The Thunderbolt didn't panic. It didn't shudder apart. It went faster. Faster than the German fighters could safely follow. Faster than many pilots believed a propeller-driven aircraft should ever travel. The cockpit would tremble. The controls would lock. The world outside would blur. Some pilots remembered the sound, a low moaning like wind pressing against the steel door. Others remembered the feeling, their stomach rising, their breath trapped, and their hands gripping a stake that refused to move. But the wings stayed firm. Even in the worst dives, test films later showed only minor flexing, not the catastrophic failures expected at such speeds. Engineers at Republic had predicted it. German mechanics were now witnessing it, and Thunderbolt pilots trusted it. Back in the hangar, as twilight bled in through the windows, the final panel was reattached. The metallic click of latches echoed softly. Tools were returned to cabinets. Someone shut out the portable lamps. The main overhead lights dimmed, casting long shadows across the floor. The senior engineer stepped toward the wing one last time. He placed his hand on the metal surface, not to study it, but as a quiet gesture of respect. The cold aluminum carried a story that stretched across oceans, factories, test centers, and battlefields. A story forged by the demands of a global war and the desperation of pilots who needed machines that wouldn't fail them. He exhaled and spoke to no one in particular. This is why we are losing the high-speed fight. No one argued. They didn't need to. The evidence was all around them. As the mechanics filed out, the engineer remained behind. The hangar door rattled again in the wind. He stared at the Thunderbolt as shadows climbed up its fuselage. In that moment, he wasn't thinking about aerodynamics or metallurgy. He was thinking about the men who had built it. Engineers who knew that air combat at 25,000 feet wasn't a game of agility, but a battle of physics. Men who understood that survival required more than maneuverability. It required strength. He turned off the final light. The hangar went dark, leaving only the outline of the Thunderbolt illuminated by the faint glow of dusk from the open doorway. Far above the western front, the sky belonged to speed. Thunderbolts descended through contrails, their wings slicing through thin air. German fighters would take positions, dive hard, and then the limit. Buffeting, vibrations, the edge of what their aircraft could endure. More than one pilot wrote in his diary about the frustration of watching a B-47 pull away below, the American plane shrinking into a speck they dared not chase. From the ground, Spotters sometimes saw the diving Thunderbolts appear like streaks, falling faster than expected. Radar operators reported targets descending at improbable rates, then recovering cleanly, climbing back to altitude and rejoining their groups. And in those moments, the war in the air shifted. Not because of a single dogfight, not because of a single tactic, but because of something built deep inside the wings of a machine most Germans had underestimated. Strength became maneuver. Maneuver became survival. Survival became dominance. Back in the hangar, as the final scraps of daylight faded from the hangar in our story, and the ghostly outline of the Thunderbolt merges with the coming night, we're left with a simple reminder. Innovation isn't always elegant. Sometimes it's heavy. Sometimes it's strange. Sometimes it looks wrong until the moment it proves itself right. But when it saves a life, when it changes the sky, when it forces the enemy to question everything they thought they understood, that is when a machine becomes more than metal. It becomes a turning point. And maybe, as you think about this remarkable aircraft, this improbable hero of physics and force, you might wonder something too. In a world pushing the limits of speed and technology every day, what lessons from the Thunderbolt still matter now? It's a question worth reflecting on, and one worth discussing. Because history doesn't just tell us where we came from, it tells us what kind of wings we might need next.